mention a few spectral line emission mechanisms, but I'm sure you will be familiar with those, so I'll do that very quickly. There's a few topics that we discussed. One is continuum subtraction, meaning the separation of the continuum emission from the line emission in your data set. Another topic is Barolo, so modeling your data cube and kinematics. And the last topic is source detection, so PIA, that I will introduce, but then Thijs will take over to show all the details of SOPHIA. Okay. Spectral line interferometry. It's basically the same as what you do with views, for example. You get a three-dimensional data set. Two coordinates are spatial on the sky, of course, and the third is wavelength. Well, in the case of radio, we talk in frequency, but because of the Doppler effect, of course, frequency is equivalent to velocity. So we have this three-dimensional data set, we call it data cube, and that's your that comes out of the telescope. This is an example, RA deck. This is frequency. All these spots are galaxies, H1 in galaxies detected in the volume. This big black square is the H1 of our own galaxy. So that's everywhere, of course. So that fills the entire part of the sky. So we're doing integral field spectroscopy. This is just an example of what such a data cube looks like. This is data cube of Mark Verheijen. Every yellow spot that you see in the cube is a galaxy detected in H1. So this is sort of nowadays with Meerkat, where you can observe over a large range of frequencies. This is what typically comes out of an observation. So a large number of galaxies that you can detect in this volume. So this is, and it's also important to really consider the data set as a three-dimensional data set, not as a sequence of images, which it is, of course, but it's also important to look at the cube in different planes, like, for example, right ascension, velocity. So to understand your data, to really think of it as a three-dimensional data set. Before that, just very briefly, the main radiation mechanism that we observe in the radio domain, and I'm sure you're familiar with it, atomic hydrogen, that you observe the low density cold ISM, temperatures 100 to 5000 Kelvin. Then, of course, there are many molecules. There's also the cold ISM, really cold ISM, masers, OH and water, for example, they have maser lines. And I'll mention the recombination lines. It's something that people usually overlook. That's the ionized ISM, the H2 nature kind of conditions. And of course, it's a wide range of astronomy that you can do. Physics of ISM, star formation, galaxy structure, evolution. And in principle, from within our galaxy, so really local, and in principle to the highest redshift. So like in particular ALMA, you can detect galaxies easily at redshift 4, 5, 6, 7 in molecules. Not in H1, unfortunately, but in the molecules you can do. And also at very low resolution, say arc-minute resolution if you want, to very high spatial resolution. The highest spatial resolution, say micro-arc-second resolution, is achievable in the radio domain. 21 centimeter, famous of course, is the ground state of hydrogen. The lowest level is split in two levels, depending on the relative spin of the electron of the proton. And when the electron flips, it emits a photon of this energy. It's one of the most accurate quantities known. Not the most accurate, but one of the most accurate quantities known, because it only depends on atomic constants. The physics of this is relatively simple. So this is one of the most accurate quantities known. So you get a photon of 1420 megahertz, 21 centimeter. The disadvantage is that the Einstein A is 10 to the minus 15 seconds. That means that if an atom is in the upper state, it takes about 11 million years for it to flip. And that's a long time. So a cloud of H1, an H1 atom doesn't emit much. Fortunately, there are 10 to the 66 hydrogen atoms in the galaxy, so you can still see it. Still, you're limited to relatively low redshift in emission. So the highest redshift detection of H1 in emission, there are now stories that it's 0.06. But that, of course, in these days when James Webb looks at redshift 15 or whatever, 0.04 is, of course, well, not a local universe, but nearby. Still, redshift 1.6 is 6 key years look-back time, so it's almost a half of the universe. The boring half of the very little happens, but still, so it looks redshift is low, but the look-back time can be considerable. And what you observe, of course, H1 in galaxies, classic, because in H1, the universe is very different. And this is an optical image, radio H1 image, same scale, and it looks very different distribution. We used to say that the H1 goes out to much larger radii, but Thijs and I have shown images today, or a few days ago here, by Trujillo, that that's not really true. If you really go deep, you also see optical emission here. So, but it looks very different. And of course, what you do is the kinematics in this data cube. And you get, this is a movie of channels of a galaxy, H1, and you can nicely detect how the emission changes the frequency. You can translate that into a velocity field, and you can do your analysis of dark matter, rotation curves, etc. That's a classic example of H1 astronomy. I also want to mention absorption. Absorption, of course, in principle, you can detect very high redshift. As long as there is a continuum source that's bright enough, you can detect it. And also, in principle, also at very high resolution, say tens of microarc second resolution, in principle, but it's only absorption. Cold gas that's in front of a bright radio source. This is an example of an outflow, H1 outflow driven by the AGN. And in principle, you can do that at very high redshift. Molecules, the physics of the H1 line is very simple. There's only one transition, and it's usually optically thin. So there's not a lot of physics you can do with H1. For molecules, that's very different. Because molecules are much more complex. All these heavy molecules, and this is the same molecule, different types of transitions, vibrations, mutations, whatever. So one particular molecule, for example, CO, has already a very rich spectrum. And then, of course, there are many different molecules. I believe there are more than 200 different molecules identified, and many still unidentified. This is an ALMA spectrum with emission lines of molecules. It must be terrible to analyze this kind of spectrum. It's enormously rich in information. Of course, we used to do kinematics, but because you all have all these different transitions and different molecules, you can do a lot of physics with the ISM, you can use line relations of the same molecule, so different transitions of the same molecule, or transitions of different molecules. And all these transitions, they depend on temperature, density, optical depth, abundance, whatever you need, radiation field, etc. So there's a lot of physics in it. Very complicated also, of course, but you can do a lot with it. And this is just an example, ALMA observation of an AGN, 3C84. This is a CO, HCN, and HCl plus. Similar depth, you can see that this is a circumnuclear disk around the AGN. And you can see that the circumnuclear disk is about equally bright in the three transitions, but these filaments that are streaming through the circumnuclear disk are very much brighter in CO than in the other molecules. So you get a very good picture of the physical conditions and how they change around this AGN from this observations of molecules. One thing I want to mention, and it's not mentioned very often, are radio recombination lines. And they are simply the radio equivalent to, say, H alpha. It's a hydrogen atom at some level, and it drops, say, 1 down, and H alpha goes from 3 to 2. Of course, there are an infinite number of levels in a hydrogen atom. And if it pops, say, for example, from level 92 to 91, it also emits a photon. and it's called the alpha photon because you pop only one level. But because you're higher up in the atom, in the energy levels, the photon is at radio frequencies. And there is a very large number of these radio recombination lines detectable, so level 92 or 166 beta, about 2 levels. This is a typical example of such a spectrum. This is the H alpha, 90 alpha recombination line, but also helium and carbon and other ions, atoms, they do the same. So this is the blend of the helium and carbon recombination line. This occurs in the ionized ISM and is very useful for studying H2 regions, for example. And one of the few things is that there is a very large number. This is observations we did in Westerbork of a certain bandwidth. This is 166, 167, 68, 69, 170 alpha. They occur in your observing band is broad enough to detect all of them because they occur every 24 megahertz. And you can stack them. So this is then the average. This is the true thing of these recombination lines. If your band is broad enough, you detect several of them, and you can improve your signal to noise, the solving here. And it's very good diagnostic of temperature of the warm ISM. And the properties, whether they are in emission or in absorption, depends on many physical parameters. So it's a really good tool for studying the ionized ISM. Then to the technical part. This is a slide I showed on Monday, Tuesday. How does the interferometer work? This is the same slide. And what we do, we have a signal of one antenna, second antenna, we combine the correlator. We get a quantity that's called the visibility. It's a complex number because it measures the amplitude of the signal, of course. Plus, it also measures this time delay between the arrival times between the two dishes, and which depends on where the source is on the sky. So it's a complex number. And if you measure enough of these visibilities, you can make your image, because these visibilities are the Fourier transform of the sky distribution. So this is a monochromatic case, but you can, in principle, it's not so difficult, add to this machinery. I will not discuss, but you can add to this machinery that you get this as function of frequency. So out of your interferometer is not one number, one visibility, but the visibility as function of frequency, which, of course, is the Fourier transform of the sky as function of frequency. And then, of course, you can invert with the inverse Fourier transform, as we discussed before. So you can make images as function of frequency, which is your data cube. This can lead to very large data sets. So America, for example, which is in terms of H1, the main workhorse at the moment, you can produce more than 32,000 channels. Each channel covers about a degree on the sky. So these are huge data sets. One single observation of a few hours is several terabytes. So it's computational demanding, not complicated. The techniques that you apply are the same that we applied 20 years ago, but the data volume has really exploded. But this is sort of, for H1, the state of the art. ALMA has fewer channels, although an upgrade is in progress for ALMA. ALMA will also produce very much larger data volumes in the near future. Also, one option is to have more channels. So, very large data volumes. That's a consequence of the modern technology. Such a data cube, of course, every channel is a picture of the sky at a certain frequency. And of course, there are many different frequencies. That data cube contains, of course, a mix of line emission and continuum emission. And this is a movie of a data cube. And this is a small data cube. And you can see these black sticks. That's the continuum emission, because that's basically independent of frequency, equally bright at every frequency. And in between, you see this mess. This is the H1. And obviously, if you want to study only the H1. You don't care about continuum. You have to get rid of the continuum because it's noise. So this is a step you always have to do, either with ALMA or meerkat or whatever. And I will explain how you can do that. What's the common way of doing it? This is a movie from Westerbork of the dirty data cube. So this is just the visibilities, Fourier transform, no cleaning, no nothing. And you can see here are continuum sources, and these are the rings of the PSF. And we have this ugly PSF in the radio. So this image is covered with continuum sources, but in particular, the grating rings, as we call them, the PSF of continuum sources. If you look carefully, at some point, there is a little bit of line emission. Yeah, if you see, there's a little bit of line emission, but it's completely swamped by the continuum, and in particular by the PSF of these continuum sources. So we want to get rid of these continuum sources. This top panel here is a slice through the data cube. So this is light ascension frequency, so through the middle. And you can see all these vertical stripes, those are these continuum sources and the PSF of the continuum sources. And all these vertical stripes, and you can see here, there's a little bit of emission. So there are a number of ways to separate the two. A very simple one is shown here. This here upper plot is a spectrum, so it's at 1 pixel here in the middle, and it shows the spectrum in that data cube. So there is here, you can see the spectral line, and here is sort of the continuous level of the continuum or of the PSF. And what you do, then you blend, it's very simple, you blend the channels where there's the line emission, you fit a polynomial through the rest, and you subtract. So you get this. Now, and you can see there is a slope, and there's also a certain offset. That slope and that offset has been removed. So the continuum at that pixel has been removed. And you do that for every pixel in the data. And then you get this. So this is the same slice as this after this process of fitting the continuum through a simple polynomial. So this is an agnostic technique. It doesn't know whatever is here, whether it's a source or PSF. It doesn't care about it. It's completely agnostic. It doesn't have a concept of source or PSF. It's just you look at the data, there's a slope, you fit something, and it disappears. Yeah, this is a very simple technique that works very well with ALMA, for example, and but not so much anymore with meerkat because this only works over limited bandwidth. Because the typical spectrum that you have here, if you have a very broad band, you cannot approximate with a polynomial anymore. It's very bumpy, all kinds of things. So you cannot fit the polynomial anymore. But for ALMA, this still works quite well. So this is an agnostic way of subtracting the continuum. It doesn't matter whether it's source or PSF. It also doesn't matter. Suppose there are errors in the calibration that are frequency independent. So these PSF are wrong. But if they are wrong in the same way in every channel, those errors also disappear. Yeah. And that's useful because in general, the signal to noise of the continuum is much higher than the line. So if the level of calibration is not sufficient to do your continuum science, it may be sufficient to do your line science because the sources are much fainter and thus also the level of errors is much lower. And with this technique, you don't have to bother sometimes about the errors in the continuum because although the line will have the same kind of errors, you will not see them. They are below the noise level. So this is a very useful technique. So this is the movie I showed before, and so it's not cleaned with continuum. So this is really the dirty image, and this is after this fitting polynomial to the spectrum. And you can see all the continuum and all the rings have disappeared. And what I see now is at some point the emission of the line emission of the galaxy. Clearly, it has still the PSF, the dirty PSF around it because I haven't cleaned yet. But now I can simply clean only the channels where there's line emission, the same cleaning algorithm I did mention before, to get this cleaned data cube. So this is the final cube. Continuum has gone, has been subtracted. The remaining line emission has been cleaned, and you have a nice data cube that you can do your science with. Because in principle, you could clean every cube, every channel of the cube, every 32,000 channels, you clean all these continuum sources and subtract them. Then, if you're only interested in lining, you don't have to do that. You subtract the continuum just in this agnostic way, and you remove it perfectly, and you get a nice data cube of the H1 in a particular galaxy. So this is the simple thing. So what I illustrated is that you fit here in every pixel in the data cube, you do this process. You can also do it on the visibility, because every visibility is also a spectrum. And because you get as visibility as function of frequency, you can do the same process also on those spectra. So you can subtract the continuum before you make the cube. It is more or less equivalent. It's more or less the same. It's not in detail not, but there's very little difference whether you do this subtraction before or after making the cube. So if you would do the subtraction before making the cube, so you do the subtraction on the visibilities, and then you do Fourier transform, you will get this one. And it's basically equivalent. So this polynomial fit, if you do it in the UV domain, it's generally called UV-lin. You fit a polynomial to the spectra in the UV domain. If you do it in the image domain, we call it in-lin, basically the same. The advantage is that it's insensitive to errors that are only time dependent. So frequency independent errors also disappear. That's a property of both these techniques because they are agnostic. They don't know what is a source or what is an error or whatever. The big problem is it only works over limited bandwidth because you approximate a spectrum with a polynomial, but if you go to large bandwidths, that spectrum is not a polynomial anymore. It's all kinds of bumpy stuff. So that doesn't work. So one thing that does work in the sense that you can do it over very broad bandwidth, that's called UV model. We mentioned before, that you can clean, if you clean your image, your continuum image in this case, of the same observation, you make the continuum image. So basically, you average all the channels, you clean, and the result of that clean is this list of delta functions. Well, that, in effect, is a model of the sky. And every delta function corresponds to a source, so you have a model of the sky. So what you do, this list of delta functions, you transform back to the UV plane and subtract it from your data. And because that you can do exact, this works over very wide bandwidths. The problem is, it does not handle the errors, because your model of the sky is only the sources. If there are still errors, they are not in your model. So you will subtract the sources, but not their errors. So you're between a rock and a hard place in, say, Australia. And one technique works very well with wide bandwidths, but you suffer still from errors, or you narrow band, but the errors are. So what you do in practical, you do both. First, you do this, because you get anyway, for your calibration, you make this model. If you do the self-calibration of the data, you have this model. So why not subtract it? It's for free. And then the remaining residuals, due to these errors that are still there, you can clean them up with UV-lin or IM-lin. That's the standard technique. One warning about this UV-lin or IM-lin. So you have this spectrum, you blank the channels where it's the line emission, and you fit a polynomial the remaining. Don't overfit. Use an order as long as possible. Say, for example, a straight line is sufficient, but you fit a second order or a third order polynomial over. And it's unconstrained over this range of the line emission. And you blank, you don't fit to that. The fit can do this, class, because there are no constraints. So this is the same data. This is when I fit all to this. This is a position velocity map. And every position I fitted a straight line, say first order, and here second order. And you can see, so I haven't fit over this range, and you can see that this flapping of my second degree polynomial, second order polynomial, has created residuals in it. And what can happen, because now everywhere in the spectral range where there is line emission, your baseline is doing this. So what can happen, you say, oh, I look at the spectrum there, look at this. Absorption. But it's not absorption. It's continuum that has been subtracted in the wrong way. So be careful about this. This is, well, not a common mistake, but it happens. So if you don't do it in a correct way, spurious absorption may result. Simply because of this flapping of the baseline. Another error that I want to point out for ALMA users, ALMA pipeline does detect a continuum in this way, but it does it in a particular way. Usually with ALMA you observe with 4 spectral windows. And instead of doing this operation for each spectral window separately, it combines the 4. It makes a common fit to the 4 spectral windows. That doesn't always work. This is an example. This comes from the ALMA pipeline. Here is the nice emission. And here there are strong residuals remaining from the continuum subtraction because this algorithm doesn't always work. So if you get a Q from the ALMA archive, be aware, check this, because this can happen. You can fix it by just fitting again, but you should do that. You should not leave it in. So this is a thing that I ran into with ALMA several times. So be aware of that. Last point on continuum subtraction. So over very wide bands, this polynomial fitting doesn't work anymore. So you need an extra step. You need a different step. This is from a wake-up observation, very broad band, very strong source. It was a 5-density source, a really very strong source. We make the continuum image, we make the continuum model for the calibration, etc., and we subtract it. And this is then what is left. You see, the spectrum is still a little bit wobbly. And these are just due to the errors remaining. This is an extremely bright source, so it's almost impossible to get it right with the self-calibration. It's still the amplitude is 0.1%, so it's quite good. But you still want to get rid of this. And one trick is, so you need, instead of fitting a polynomial, and you cannot fit a polynomial to this because a polynomial of a certain order is bumpy, but the spacing between the bumps is more or less the same. And you can clearly see that the spacing between the bumps here is not the same. So you simply cannot fit a polynomial or extremely high order. So you need something that fits the local properties of the spectrum. Things that people use are cubic splines. So you fit a polynomial and you define a few points and you fit a nice smooth polynomial through those points. Or what I use is what's called the Saritzky-Golay filter. It sounds very complicated, but it's very simple. What you do, it has 2 parameters. One is the number for each point in each channel. You define 2 numbers. One is the width, say 20 channels. The second parameter that you define is the order of the polynomial. So what you do, of this 20 channels around that point, you fit a low order polynomial. And now it works well because we have reduced the problem to small bandwidth. So now this fitting of polynomial works. And you get an interpolated value for your channel. And you do this for every channel. And then you get a smooth red curve, and you locally fit this polynomial. And you subtract, and you get a very nice spectrum with a nice absorption line. So this now, because of the broadbands, for example, for Beerkracht, you have to do this kind of techniques that are required because of the bandwidth.
Presumably, you also need to use the lowest order polynomial possible.
Yes, yeah. still. These two parameters, one is the width is also important. Of course, if you take a width that is much larger than 1, then it still doesn't work. You can play with it. It's very fast. Because in principle, you fit a polynomial at a point, but you can write it as a convolution smoothing. So you don't actually have to do the fitting. You just run a filter over your spectrum in a millisecond, and it's done. It's very fast. Oh, this is the fitting. So this is just an arbitrary curve. And what you see is it fits for every point, it fits to the red part, the polynomial of, well, second order probably, and it replaces that. And you get this nice, you get a smoother version of your spectrum. But that's now required for the broad bandwidth to solve that.
Just add one thing. So I just wanted to connect all this continuum subtraction with what I mentioned on Tuesday, the first time. So the H1 people, they get rid of the continuum, and it's very annoying, this continuum. And how can I get rid of it in the best way? But with that continuum, you can then do other things. So, okay, you want to subtract it, but then you can also use it. There seems to be always two communities, one that is only focused on the continuum, one that is only focused on the line. But in fact, especially with this telescope with the pen, you can use both. And so you can explore your continuum to see what maybe there is an interesting radio source, or maybe you can do the star formation rate or whatever. So it's not only annoying, it can also be useful. But I just wanted to connect the two.
But example, you may remember this example that I showed as, say, if you flag too many short baselines that for certain frequencies the source disappears. That's a very interesting source from the continuum point of view, and people have written a paper on it. But the original observation was done for the spectral line, for the H1, not for the continuum. So we can use the same data set for both continuum and line. In that case, it turned out to mean that the continuum is interesting and separate science, but on the same data set. Data analysis. So we have the data cube, and we want to do science with it. So we can, of course, map the brightness distribution. So effectively, we integrate over frequency to get the total line emission, and you get a map of the H1 distribution in this case of the galaxy. Same for the velocity. You can, for every pixel, you somehow define this is the velocity. The velocity I observe, and so this is the velocity field of that galaxy. And then you can do science, like in this case, a rotation curve, mass modeling, etc. One aspect is, of course, to do the kinematics. And we want to translate, like in this case, and this case, this is the velocity field. From this velocity field, we want to get this rotation curve, and the rotation velocity is function of radius from the center. And then we model with the optical disk, the H1 disk, and the diametric cable. So how do we go from this velocity field, from the kinematics, to these rotation curves? So this is an example, famous example, ETC 5055, famous for the warp. This is one of the famous warp galaxies. This is the optical, the H1 intensity, H1 contours on the optical, and this is the velocity field. And you can see the velocity field is a nice twist. And in this case, the model is that it's a warp galaxy. So what you see here in the kinematics is this changing orientation of the disk. And the standard way of modeling that is to divide the disk in rings. Each ring has an orientation, inclination, position angle. Each ring has a rotation velocity. If you want, also a radial velocity, but in general, and certainly in the beginning, you'll see that there are no radial motions, so this term you forget. So each ring has a rotation, inclination, and position angle. You make a model, and you can fit that to the velocity field, and you get the rotation, you get the inclination, position and the rotation velocity is function of radius. That's your mass model. And this is the old approach to do that on the 2D velocity field. So first you make a velocity field and then you do this kinematic analysis. And in this case, that works quite well because the galaxy is quite well resolved. And the beam is quite sharp. So we can do it, and this is then what comes out in this case. This is the position angle, inclination, and rotation velocity. You can see that the position angle and the inclination vary with radius, but this is the wall. All fine, this works. However, of course, there is a problem for galaxies that are not well resolved. The problem of beam smearing. So this is an example. This is an existing galaxy 2403. This is as observed, the H1 velocity field, as observed with the VLA, with a resolution of 15 arc seconds. So taking that data, this is how it would look if you would observe a single dish in the GBT with a resolution of almost 10 arc minutes. And you see all these velocity gradients, and of course the galaxies get bigger because the beam smears it out to larger area. But you also see that here the velocity gradients get smeared out. And the gradient here is much sharper than in this region. And you can also see that in the dispersion, this is the velocity dispersion, so the width of your line. And in the GBT, is a very large peak in profile width. But that's just because all these different rotation velocities are grouped together. So if you would fit such a tilted ring model, this velocity field, you will get the wrong answer because the velocity gradients in the center get smeared out. They disappear from your data. And this is an example of a few galaxies. The blue line is say, the true rotation velocity as determined from high resolution H1 observations. So then this data cube is convolved to lower resolution, the resolution of the GBT. And if you then make the velocity field, this green dots then is the rotation velocity you get by fitting a tilted ring model to the velocity field of this low resolution cube. And you see you're completely wrong, completely off. Rotation velocity is too low, and the velocity dispersion is way too high. What you can do, of course, is not fit it to the two-dimensional velocity field, but to the three-dimensional data cube. So your tilted ring model, every ring has a certain orientation and rotation velocity. You compute how that ring would appear in your 3D data cube. That is just geometry, it's not complicated. And so you create a model data cube, you convolve the resolution of your VLA, of your observation. And then you do the fit in that domain. So you fit to the three-dimensional data cube. And the difference is that in that data cube now, the smoothing due to the resolution is taken into account. It's in your model. And if you do that, you get these attack points. And you can see that even though the resolution is very low, with this technique of this 3D fitting, you recover the correct rotation velocity. So this is very important. For example, ALMA is detecting galaxy disks at redshift 4, and they are only a few beams in size. You have to use this kind of technique. So now this is a famous parole, and several of you must have used it, of course. But this is the way to do. Want to make a few remarks on this, how to use it. It's not completely straightforward to use it. The way I do it is first I do a fit with all parameters V. I try to make some initial guesses, where is the center, what is roughly the inclination, etc. You provide, you do a first initial fit, and the result of that fit is the central position in the systemic velocity. You don't care about the rotation curve yet. So this is the position now. Then you do a second fit, but now you keep these parameters fixed. The idea is to remove as much as freedom in the fitting. So if a parameter you can keep fixed, keep it fixed. So the first fit, free, and you determine these three parameters. Then you do a second fit with only, say, the inclination, position angle, rotation velocity, free. You get a second fit. And you look at it and say, well, maybe you do a third fit. For example, you keep the position angle fixed. And because you're in the inner region of your galaxy, usually they are flat. And in the inner region, the optical disk seldom has a wall. So we keep it fixed. Just to reduce as much the freedom in fitting. Because you're fitting a large number of parameters. So maybe 15 rings, each ring has 3, 4, 5 parameters. So there's an enormous number of parameters. So try to reduce it. One thing you always have to do, fit the receding and the approaching side separately. If the galaxy is regular, symmetric, you should find the same. And the rotation curves, etc., should be the same. If they are not, the galaxy is not symmetric. And you get an idea of the errors in your fitting. And what is, for example, you compare the two rotation curves from the receding and the approaching side, and you see a typical difference. Well, that's then the error in your rotation velocity. Because one problem with Barolo is this does give error estimates, but they are not very good. They are pure statistical error estimates, and they do not really reflect the uncertainty in the parameters. They are working on it, on a Bayesian version of it, because then you sample the error distribution, you get a better idea of the errors. But this is a weakness of Barolo. Important diagnostic. Barolo makes a few plots after you run it. And an important diagnostic is this bottom one. One of the plots it produces is a position velocity diagram along the major axis and along the minor axis with the model on top. So see the major axis, our model is the model is right on top of the data. The thing to check is the minor axis. If the model is correct, it should be always even. So if there's an offset or tilt or whatever, you have to look again, and this is an important diagnostic. The position velocity plot along the minor axis. Of course, you should look, and this is I will show this afternoon. Compare your model cube, and the Barolo also produces a model cube, with your observed one. Not only, and this is the right ascension declination, and the blue is the data, and red is the model, and you can compare, but also in position velocity maps. Those are more informative in general about the quality of the fit. So this is a right ascension velocity, so this is a horizontal slice through the data cube, and you see, well, the model corresponds quite well with the data. This is along the minor axis, so this is the declination velocity. That reasonably well, slight mismatch. Don't get immediately excited by small differences because galaxies are rarely really symmetric. So if I would only see this, I would not get excited. Here, this is another position velocity diagram. This is the galaxy, by the way. This is made into, somebody suggested made into cube. Is the person in the audience or?
No, someone in the registration form. I think 2 people mentioned the
This is this galaxy. I did it.
No, other people suggest. I would like to say similar or the Malin too.
So this is the total H1 that I made with Sophia, the telescope stuff. This is a center, you can see it's an asymmetric. Yeah, see it's not. But if you compare here, this is a PV diagram, so a little below the center, you see this blob that really stands out. This is not in the model. And if I look more carefully at this cube, I think there's another, either a companion or something else on top of this galaxy. I don't know. This is data from 95, so people must know this. But you can clearly see this kind of thing. If you see this, then it becomes interesting. Last thing, data analysis that I will quickly talk about. So this is the kinematics. The other one is how do you make this, the total H1. So the standard way is that you have this 3D data cube. You can compute the total flux, and so the integral is a function of frequency or velocity. The intensity weighted mean velocity, so this is more or less the velocity of the peak, basically, or the width of the line, the dispersion. And these are just the statistical moments. So this is called moment analysis. And this is a standard way to parameterize the emission in the data cube. It's simple, we take your spectrum, and you compute these quantities, and that produces this velocity field and the total H1 number. An alternative would be to fit Gaussians, and then your Gaussian also gives these parameters, but profiles are not always Gaussian. So that does not always work. So this looks very simple, but it is more reliable in general. So this is then what you get out of it. This is then the zero moment, first moment, second moment, and you can do your science. Okay, so I take my cube and I integrate these moments over my data volume, and this is what I get. It's not good. Obvious reasons. This is the total H1 if I just integrate blindly every channel. This is the velocity field, and this is dispersion. And you see, this is not as good as it was before. So why is this? Very simple reason. So this is a spectrum in one of the pixels of this data cube. And there's 0 here, and here is the line emission. If I compute simply blindly, say the total H1 emission, I integrate this profile. The line emission is only in a few channels, and the noise is everywhere. So I add a lot more noise than I should. And obviously, I should only integrate over where there's the emission. Because if I integrate over the entire spectrum, this greatly reduces the signal to noise. And it gets even worse for the higher the second order moment is terrible. So what you have to do is obviously define in some way, and this is Sophia, some way that you calculate only these moments over the range where you think there's emission. Okay? It's called wiggling. And then, of course, if you do that for every pixel correctly, you get the right result. So you can do that defining for you can do with every spectrum. You can do the same in principle in a channel. This is a channel of the same data, and you can say, oh, this is all noise, and here this emission. So you make a mask in the image, and this is the emission. So it doesn't matter how you do it. You do both if you want. Somehow you create a three-dimensional mask that inside the mask is the emission, and outside the mask there's only noise. And then you get this. If you then do this integration, this moment analysis, you get these nice maps that I showed before. As an introduction to TAGs, how do you do this? Well, one thing, the standard thing is in H1 usually sources are extended. And the radio data, if you smooth the data spatially, you improve the signal to noise of extended emission. Yeah. One small detail in the radio data. So if you smooth your data to lower resolution, the noise increases. Not decreases, increases. It's very simple. You have your telescope with baselines. If you reduce the resolution of your data, you throw away the information of the longest baselines because they contribute to the resolution, the high resolution of your image. So you throw away telescope. You throw away collecting area. So it increases because we have density per beam, not per arc second, square arc second, or something like per pixel, we have per beam. So the characteristic of the data, the beam changes. So the noise increases. If you compute the noise in density per beam, after smoothing, the noise is higher, should be higher. Of course, the flux of an extended source increases because we have density per beam. Say you have an extended source, smooth distribution, and your beam is small, or you increase the area of the beam with a factor 2, you get twice as many density per beam in your data. So smoothing the data for an extended source, the flux increases. So if the noise increases, the flux also increases. For the extended source, this one beats the first one. So the signal to noise increases. Nevertheless, this is an important thing to realize, that smoothing the radio transmission, the noise increases. So this is a channel, resolution 15 arcseconds. This is smooth to 30 arcseconds, same intensity scale. And you can see that the signal to noise of the emission has increased. You can also see that the noise has increased. But the signal to noise is much better. So what you do in general is you take your data cube, you smooth it to lower resolution, typically factor 2. You determine the noise properties of that smooth cube, and you define a mask, say 2 sigma, 3 sigma, whatever number. So that creates a mask, and that mask you apply to the high resolution. You define the mask on the low resolution cube, but you apply it to the high resolution. So you lose, but you don't lose the resolution in your data. And this is then what you get. So this is, if I would take my full resolution cube and I clip it at 3 sigma. Full resolution, 3 sigma, the noise of the full resolution cube, and then I add the channels. So I see some galaxy, but I see also a lot of noise peaks. This is when I do the smoothing, define the mask on the smooth cube, also 3 sigma, but then on the smooth cube, and apply that mask to the original, then I get this one. You can see, certainly in the outer regions, I see a lot more H1. So this smoothing helps to improve the signal to noise of extended emission, and you can better mask the data. Of course, you can also do the same in velocity. So you not only smooth spatially, but you can also smooth in velocity. Nice detail, smoothing in velocity, noise decreases. Because the unit is per hertz. So that's an instrument independent unit. In the image we have per beam, which is instrument dependent. So if I smooth in velocity, the noise decreases. Because I have per hertz, not per channel or per resolution. You do the same, you can smooth in velocity, and here the same, you can see this is smooth, just a simple smoothing in velocity, and you have a much better definition of the signal. So you do smooth spatially and in velocity. Question is then, how much do I smooth the data? I said, well, typically a factor 2. Well, in principle, you should smooth to the scale of the emission that you want to detect. The optimum resolution is the size of the clump of H1 in your image. That is the optimum signal to noise. Problem is, there is not one single scale in your image. And you have a large scale structure and a small blob. So what is then the optimum scale? So, solution is very simple. You smooth to many different resolutions. And for each resolution, you make a mask, you combine the mask, and that's your optimal mask. So every block will be picked up in one of these smoothings, not only spatially, but also in velocity. And this is what Sophia does. Now, Thijs will explain how that is quite an elaborate process, and you need a good understanding of how it works to apply, but this is the optimal way of making these monographs. So the result of Sophia is by this smoothing the data to several resolutions, spatially and in velocity. It constructs, it does some logic about the mask, etc. It makes sort of an optimum mask for your data to give you and the output is a moment 0, moment 1, moment 2 images. And now I think this is my last slide.
We'll switch.
Yeah, we'll switch. So I can shoot. On the question, sure.
Yeah, I have a question concerning the use of public data. If you have for example, data coming from things or radio bus that they give you not only the data cube but also moment 0, moment 1,
Yeah.
moment 2. And suppose you only want to get the rotation velocity curve, for example.
Yeah.
Do you really need to apply all these moment 0, moment 1, moment 2 techniques, or you can trust what they give you?
In general, yes. Yeah, AWS certainly, because I was part of AWS. I think in principle also, I have to say that the data quality of things is not always perfect, in particular for the very large sources like M101, for example. M101 is almost a degree in size. And the map on the things, moment 0 map, is smaller. And it's quite difficult to make a good moment 0 map of such a large object. So you do see in the literature that they take the data cube from, or the data from things and repeat the exercise themselves. In general, but that's certainly not true for every galaxy. Many of the galaxies or things are okay. But it's good to have a critical eye on the data quality. For example, I mentioned this negative hole thing, and they have not cleaned deep enough. For some of the data sets in things, that is the case. Be critical, and you do see in the literature that people go back to the UV data and do it themselves. And you can significantly improve. So, but in general, there's mongoose. I don't know whether you're interested in mongoose. Those they are very good. So in general, I would say yes. ALMA, I do have experience with ALMA that for extended sources, the cleaning is not deep enough. So then, same. So ALMA is relatively easy to do yourself a bit better, because you get the beams at out. And it's also quite easy to regenerate it. You can also get a script and ALMA. Be critical, but in general, the answer is yes, but you should check.
Question. So regarding 3D Barolo, I understand that the use of it for, when you say that data, the beam size is quite large, so you want to get intrinsic kinematics and stuff. That are because you build in a 3D model, you get the intensities, the velocities, and the dispersions all in one go. Yeah. But in principle, there's nothing preventing you, if you were interested in velocities only, there's nothing preventing you to do the classical tilted ring, but then convolving that model with whatever beam size.
Yeah, but not on the velocity field, because because if the gradients are significant over your resolution, you will certainly underestimate the rotation velocity. So,
but can you just build the tilted ring and then convolve that model?
Yeah, this is what Barolo does. It takes a tilted ring. Each ring, it computes where the emission along those rings ends up in the data cube, and then convolves it spatial velocity and resolution also. And that three-dimensional model cube is compared to the data, chi-square, with an output. But that convolution to the resolution of the data is important. You will, the example I showed is quite dramatic. You go from 15 arc seconds to 10 arc minutes. That's just to illustrate that it works. But even if you would go from 15 arc seconds to 30 arc seconds, you would already see the effect.
So you said that Barolo does the convolution both spatially and also in velocity.
Yeah.
Why in velocity and how is that done?
Oh, because you can fit also the velocity dispersion with Barolo. And you have to take into account also the instrumental resolution. It can be that your resolution, instead of typically in the radio, the velocity resolution is larger than your channel width. So it's larger than one channel, it's typically 2-3 channels. So if you compute, you would say this cloud is here, and it has this velocity, so it ends up in this velocity in the data cube. You will have to smooth it to either, well, first also the intrinsic velocity dispersion, but also certainly the instrumental dispersion, because typically you cannot neglect the there are, so that it's important. Typically, Barolo gets these things from the header. These for the normal radio observation, this information is in the headers, like the resolution, etc. But sometimes it's not, and you have to check. But in principle, you can also get the velocity dispersion, or even also the vertical height disk. So that is not well constrained usually because it's smaller than your beam, so the signatures of that are very subtle in the data cube, so I would not trust it very much. But principally, also those parameters, radial motions can also fit. But in general, usually they are zero, just rotation, unless of course there is a bar or slide.
And from what I understood, they are working on a new version to include an outflow component on the current.
Yeah.
But it's still not released.
Plus, they are making a Bayesian properly sample the error distribution, because the errors given by Barolo, you should not test. pure statistical errors from the chi-square. And the source of error is much more in asymmetries and this kind of thing. So I would not trust those errors.
But even when they do the conversion, then you will still follow your scheme of fixing things.
Yeah, that's recommend.
If you let it everything free, I suppose there's all kinds of degeneration.
Well, yeah, you let it free and then doesn't make sense. One of the plots that Barolo produces, for every parameter, you get a plot. So you, for example, you let everything free, then you get, for example, a plot of the fitted X position as function of radius. You take a look at the scatter. And if it's a scatter, you say, okay, I'll take a constant. If it does this, and let's do something else. You can fit, then you can keep it fit. But I strongly recommend you reduce the number of parameters as much as you can. Because like I said, in principle, there are 5, 6 parameters per ring. If you have 10, 15 rings, there's a lot of space to wiggle the fit into the wrong direction.
More questions?
Okay.
Yeah, and I'll start sharing and.
Just a question. Thank you, because I have to, if we are going to be late for the coffee break, I just have to.
No, we should be in time.
Yeah, you should. It's okay, I
Yeah.
just have to tell them that we'll be late.
No, I think what I have is like, no, yeah. That's the work. Right.
It's very good. Now this is super, yeah. Thanks for to explain. This isn't for me.
Good.
Thank you very much.
We'll. Something. So take it over in the PDF. In the PDF.
Whatever format you think.
There you are.
PDF, you will lose the PDF.
The both.
Would be. Did you have the camera on?
Yes, if you're going to point, because.
Yeah, so I'll have to go out of screen sharing to do this. I lose my pointer. Okay, here we go. So we have to put video on. Oh, I have to change the background, I guess.
Or don't worry if this, I can put mine and they can see from mine.
Oh, okay.
Yeah.
Yeah, there's too many things I need to change to make it work. Right. Okay, that should work. You can see, yes, okay.
So as Tom already mentioned, finding the emission in your data cube is basically a question of optimal filtering. The best filter is the filter both in spatial dimensions and in the frequency dimension is the one that sort of roughly encompasses all your signal. And if you add a whole signal within that size of filter, you have the optimum signal to noise. If you make it too small, the signal to noise decreases. If you make it too large, the signal to noise decreases as well because you add more noise over a space where you have no signal. And SOFIA is trying to actually do this in a very straightforward, but I think still a clever way. And what I would like to do is basically quickly go through some of the steps that SOFIA takes so you understand what it's doing, because it's also to use SOFIA in a proper way necessary that those steps are well understood. The Sophia can do many things, but they can also do many things wrong if you don't tell it to use the right parameters. So the idea is to go through that a little bit. These are the various steps in Sophia, and I'll skip many of them. But basically, the input is a data cube, and you can add additional information. Of course, you have to provide a parameter file, and I'll get back to some of the important parameters. You can, in principle, import also a weight or a noise cube. If your noise is varying, but you know exactly what it is, you can tell Sophia how the noise varies with position within the cube, and it can take that into account. Otherwise, it will try to deduce it from the data itself. The same with weights. If you have, for example, a data cube which has been corrected for the primary beam, then the noise goes up at the edges because the sensitivity is corrected to be flat, but then the noise will go up. And then the base cube, you can actually decorrect for that. But it's better to basically give Sophia a cube with a noise profile that is as flat as possible. Then there are other things you can do. You can do continuous subtraction. The image plane continuous subtraction, Tom mentioned. So if you have residual stuff in your image that you still want to get rid of and you haven't done it yourself, then Sophia can do it for you. You can normalize the noise, and it's advisable to do that because you want to find your sources in terms of noise and a noise flat cube. You can flag some lines of sight. For example, if you have a particular source direction where there is still continuing residuals because you had a Jansky or two Jansky source there, you can basically tell Sophia to flag a little area in your entire cube, and those pixels will then be flagged and not be taken into account where you do the source find. And you can do some filtering, but I will basically look at the basic parameters which are here, which is the smooth and clip, and I'll explain that in a little more detail, and then the linking of the sources into, or the linking of the detections into sources. Here is the Sophia test data cube, which is publicly available also on the Sophia website. This is basically an illustration. You see three galaxies. This is velocity direction. So the galaxies in velocity stretched, like the many galaxies in the cube that Tom showed in the movie. Here's a galaxy that is edge on. You can see that the emission is sort of, it's connected, but the signal to noise in the middle is very low. So keep that in mind. The edge on galaxy, of course, the emission is over wide velocity range because you see the entire velocity range is not squashed by the inclination projection, but in the central part, because there's less gas there than there is in the outer parts, often the signal as a two-horn profile type of thing, the emission there is lower, and in some cases it will be very close to the noise. And so the critical thing is this one source or is this two sources? And Sophia will do either one or the other, but that depends on how you set your parameters. I'll get back to that. So I'll come back to the smoothing, but basically Sophia goes to various steps of smoothing the data over larger and larger areas, and you can set exactly how many times to smooth and over how large an area. Then it finds sources, and those sources are then through a sort of friends of friends algorithm type of thing linked together. Those detections, I should say, linked together into sources, and then you can apply a simple filter, and that is illustrated here. This is a three-dimensional space that is usually being used. This is basically the sum for each detection, the sum, the peak, and the mean that are plotted in 3 dimensions here, including the noise. So everything that is above these, at each step of smoothing, a threshold is applied. Typically, 3.5 sigma is a good number. And everything above the signal, above that threshold is called the detection. But it also can be negative. So it's both positive and negative detections. And all those detections that are then linked into sources, and I'll get back to that process, are plotted here. All the detections, and they're colored. The positive detections are red, and the negative detections are blue. And of course, noise, if it's really Gaussian noise, will basically occupy the same volume in this three-dimensional space. And what you see here, all these clouds of points, with this cloud of points, is basically both positive and negative detections. Here, and they're already colored yellow, are all the sources that are in a different part of this three-dimensional space. And what the reliability filter does is it basically, for each source, looks at the environment, and you can set how large that environment is chosen in the three-dimensional space. And if the number of positive detections is much larger than the number of negative detections, it calculates the reliability. And I'll come back to that. And these sources all have a reliability above 90%. Those then are all the detected sources, and that is put in a catalog, and for each source is calculated the total flux. You can actually make the various moment maps. Zeroth moment, first moment, second moment is plotted here, and it will also produce a position velocity diagram along the major axis, as long as the galaxy is resolved. If it's not resolved, then of course the major axis is not relevant terminal. And the output then is a catalog of all those sources with flux and position, etc., and many parameters, moment maps. A cube with the final masks. For each source, you have a three-dimensional mask, and within that mask, all the emission is added up to calculate these various moments. So that filtering that Tom explained already took place by making the masks. So when you have the moment map, most of the noise in the cube outside the velocity range where the emission is, and outside the spatial range where the emission is, has been excluded. And then if you want to, you can put this into another pipeline. This is, we'll not discuss that in detail. It's a Sophia image pipeline, which has been put together by Kelly Hess. Basically, in the first place, to process operative results, and that produces, that takes the Sophia output, the masks, and the cubelets. For each source, a little cubelet is made, and you can actually define what size cubelet you want. It takes all those cubelets and then makes an analysis of those and makes an overview where it searches the various databases for optical images, makes an overlay, makes the moment maps, and produces an integrated global profile. And that is a nice sort of step to take, because you can immediately look at the results of your sources based on the Sophia source finding. So let's now get back to how you run it. There's a large number of parameters. Those parameters by default have values that seem to work very well, but there's sort of two sets of parameters that are very important, because there you fine-tune your source fund. They're basically in a file. You can change the file and then rerun Sophia, but you can also put individual parameters on the command line. So you run it like Sophia, name of the parameter file, but you can add, for example, scfind.kernel xy and give it numbers on the command line. There also is now an interface, a GUI, and you set parameters in the GUI and then push a button and Sophia will run. That has been available since, well, about a month or two. I tested it and it seems to work. And if you want to install Sophia and need some help, I'll be around still tomorrow and can help you with it if you need some help. But anyway, those parameters are the important ones. Are the sizes of the smoothing kernel in spatial and in the frequency dimension. The spatial dimension is basically in pixels. The default is no smoothing at all, of course, 0. That's basically just takes the raw data cube, 5 pixels, 10 pixels, and in velocity, depending on what your velocity resolution is and how broad your profiles are expected to become, the default is often something like 3, 7, 15. 31 is not in the default part. This is in this example, but it's not. Another, and I'll get to that parameter that's important, is the linker. It will go through the data, smooth these various smooth versions, and then detect everything. And it will give you a number of sources, or I should say, I keep saying sources, detections. And those detections need to be linked together into single sources. Maybe I should just go to the next few slides and actually explain these steps. The finding I mentioned, the linking, and the final reliability. I think I'll skip this. This is what I explained, is you basically smooth in 2 dimensions, and it's done step by step. So first you do, say, the spatial smoothing step, but not in frequency. Then you do the spatial smoothing step and one in frequency, and so on and so forth. So all these things are combined. So here you have like not just 3, but you have well, this is 1, 2, 3, 4, 5. So it's 5 technically the smoothing steps. I can't do the calculation quickly in my head. So it's a number of smoothing steps, and here is an example. Here is the data. After the detection threshold in the raw data, you find all these, you have all these detections. So here the emission is above 3 sigma or 3.5 sigma in a contiguous area, but there are all these noise peaks, and the negatives are shown here as well. If you smooth it, you find fewer. And if you smooth it more, you find more extended and fewer. The noise is not being picked up as much as it is here. And all the masks are then combined. So basically, you have all these masks from all these various smoothing steps. And then the linker basically looks, and I'll come to that, at all these various detections and decides which belong together as one source and which don't. So all these other individual, simple, small detections are basically thrown away by the linking process, and you end up with a final mask, which in this case only has 2 sources.
Yes, can I ask a question?
Yeah.
Because it looks to me that if you just take the last iteration,
Yeah.
you'd be done, basically.
In this example, yes, not in every case.
Okay.
Yeah. And if you have a combination where you have a data cube which has extended sources and small sources, if you did only this, then you would have lost the small sources.
Right. Okay.
So the cube, for example, Tom showed, which had large sources in the foreground, small sources in the back. If you only did one mask, you would lose all the point-like sources. So you have to do all of them.
Other question?
Yeah.
Yeah. So basically, one of the steps that you're telling Sophia does is to generate a mask for the data cube, right?
Yeah.
So taking into account that there are a lot of source detection algorithms on the web page that have been tested on the optical data, is it possible to give Sophia those masks generated by other algorithms, for example?
But that's only a spatial mask. That's not a mask in frequency.
Yeah.
So, and the sources in the spectral isotopes have basically structure and frequency as well. And like a rotating galaxy, depending on what frequency you look at it, it moves. So if you took the optical mask, like for the optical galaxy, then still would, in some places, add noise where there is no signal, and vice versa. So it's an idea, but I think it wouldn't work in practice. The linking is actually very simple, and there are 2 sets of parameters that are important. There is the merging, sort of a merging length, and that basically tells you how many pixels together or how many pixels apart you would still consider one source. And that, of course, also has to do with your resolution and the size of the sources you expect. And there is a maximum size that basically tells you where to stop linking. So it's a bit like a friends of friends algorithm, where the linking length determines which near object you still put into one family. And so these parameters are important to set, the radius xy and the min size xy, which determine the smallest and the largest size. And here is an example, though, with 2 pixels for the sort of linking length. These things are put together into one source, but these are farther away, so it's a different source. And that sort of illustrates in a very simple way the linking. So those are important parameters, and I've seen people starting with Sophia getting completely wrong results by not fine-tuning those parameters. And it depends on what size source, of course, you expect to find in your data.
And if you don't know?
Sorry?
If you don't know?
If you don't know, well, that's tough. I think there is in a sense.
Because I mean, I'm guessing that most of the times you know what you're looking at, what you're looking for, but there might be areas where it's all about discovery, and I guess then your results will be very sensitive to your choice.
No, and in that sense, sometimes it's good to actually run Sophia with different parameters and see what you get, and then look at the results. That's the best way to actually sort of interact with your data and fine-tune these parameters.
This afternoon, I'll show this to some extent to how do you check the output. So read the answer is good or bad.
And I'm gonna be this afternoon, so
okay, talk about it. So coming back to the after the linking, of course, all the detections have been put together into sources, but it still contains noise. Small sources with a small range of frequency are still detections are still there, but both the negative and the positive detections are kept. And this is a two-dimensional plot of that three-dimensional space that I mentioned that basically Sophia looks at. This is the mean versus the sum. The peak is the other dimension of each detection. And all the noise is this big cloud with positive and negative detections. And here it's hard to see a little dashed sort of ellipse is a kernel. And what the reliability filter does is it looks through that space for each detection, and it looks around that detection over that kernel to see how many other detections there are. And then it calculates the reliability based basically on this simple formula, the number of positive minus the number of negative detections over the number of positive detections. So if you have only positive detections and no negative detections, reliability is 1. If you have an equal number of positive and negative detections, your reliability is 0. And if you have like 20% more positive detections, then this number is probably 0.8. So then the reliability of that detection is 0.8. That's a very simple way of doing it. And you can play with the threshold where you call things reliable. And of course, the lower you have it, the more complete you are, but the more false detections you will have. And that's always a puzzle where to put that threshold. But it works quite well. We are looking at ways to actually improve this, because it turns out if you put it high, like 90%, you'll miss things. If you put it low at say 40%, you'll have too many false detections. You need some other criteria to do this, and we're trying to work out how to do that more cleverly. I mentioned this kernel. If you make that kernel too big, things won't work well. If you make it too small, this reliability estimate will not work well either. And the way to check whether you have the right kernel is this plot which is produced. It's called the Scanlon plot. And for it's a cumulative function of the distribution of detections, positive detections, negative detections. And for Gaussian noise, the solid line is basically what you get if you basically apply this reliability criteria to Gaussian detections only consisting of Gaussian noise. And you want that kernel to be such that roughly in practice you follow that curve. If your kernel is too small, the cumulative distribution of your detections will shift this way. If it's too large, it will shift that way. And this is a way to check whether the kernel has the optimal size. If the total number of positive and negative detections is too small, it will detect that beforehand and tell you, I have not enough statistics to do it properly. So here is a sort of an illustration of the linking. These are all the detections. This is then the result after linking, and each different color is a different source. So this is on the Sophia test tube, the one that I showed in the first slide. And you can see there are already still quite a number of things that were visible in that tube and probably false detections. And after applying the reliability, it's left at only 3 detections. And this is the moment map made through those masks of the Sophia test tube. And this is an illustration of the products that in principle Sophia can produce, but then the Sophia imaging pipeline will also pick the optical data, make the overlays, and do this in a more fancy fashion. And one important thing is it's also possible to make a signal-to-noise map for each pixel. Because the noise in the mask, of course, depending on the size of the mask and the depth and frequency, the noise will not be the same at every line of sight, and therefore it's important for each line of sight to take the noise and end the signal and make a signal-to-noise map. So they have a little bit of an idea of the reliability of your moment map. So that is a new tool that is very useful to have at hand. And this is then finally an illustration of this is the GUI. Here you can set the parameters by hand, and this is the linking length, the spatial radius, 2 and 4 pixels in respectively the spatial and the velocity coordinates. And this is then the results on the test tube. I ran this the other night, and you can see this is a single source, a single color. If you make that spectral radius too small, and remember this edge-on galaxy has these 2 blobs, then Sophia will end up with this. We'll still find it, and it's reliable, but it's a different source. But it's a single galaxy, so you have to be careful, even if the detection is almost perfect, that you might have different sources in the same object. So let me stop here and basically put this on a look. Continue to share. It's important to look at the last slide, of course. Here we go. Here we go. It's important to tune your parameters to the types of sources you have in your data. And the best way is to do that interactively and look at the results, go back to the data, see how reliable your results are. So always check the data afterwards. It's a message Tom has been giving many times as well. Look at your data and look at every step to see whether you really think that the software did what you think it did and what it's supposed to do. And experiment with different parameters. Another option in Sophia, which I haven't mentioned, but you can provide a catalog of RA deck and velocities. If you, for example, have a very complete galaxy catalog of the area that you over a large redshift range of the area that you surveyed, you can give those as primers. And then basically only do detection in those lines of sight. It's a different way of going about detecting sources, but then you can basically relax many of the parameters to pick up fainter signals. With the danger that you will pick up a barely 3 sigma detection and call it a source, whereas it's really only a detection at 3 sigma, not very reliable. So let me leave this here, and if there are questions, otherwise we can go for coffee. We can continue to discuss this afternoon. And if you want help with installing Sophia, if you're interested in using it, then I can help you with that today and tomorrow.
I'm going to ask the online people if you can turn on your camera so I can take a picture of you.
I can turn this.
Some people already left, but we were 10 today. But some days we were 15. It's right.
15.
Yeah.
Okay. Well, that includes you, so 10, yeah.
Just a second, let me see, how can I visualize this? This area, no? Okay. So maybe we give them just a little bit more time. And meanwhile, I'm going to share this announcement for the radio astronomy school that we are going to have in Groningen in April next year. So the school will be on the 13th and the 14th and will be followed by the second ExGal project meeting. So if you're part of the IAC and you want to attend the radio school and the second project meeting, you are welcome. I think we are going to have some ExGal funding for students that belongs to ExGal, but if your group, you're not part of ExGal and your group cannot afford, talk to us. We can try to figure a solution, for you to attend the school. I think in this school we are going to go a bit deeper on the hardcore radio astronomy, but it would be a pleasure if you want to join.
Same applies if you're not from the IAC, also talk to us.
Yeah. And let's see if we can take this.
There is a lot of hands-on practical.
Yes.
With yourself. Yeah, understand.
Okay. So I will take the online picture. Let me see. Carlos, you don't have the camera on. It's okay. I'll put you. I'll edit later. Okay.
We have an arrow. It's an arrow. The arrow pointed.
Let me take another one. So we have here also Danielle. He's the master student that is working with the Mongoose Galaxy. Okay, so let's go. And Julia is connected from Australia, right?
Oh.
Nice.
Yes, I'm here in Sydney. It's nice to see you all there.
So thanks for joining online. We now go for a coffee break, but I hope you have a nice time. And these classes will be, we are going to record them. No, we record all of them. And next week I'll try to upload in the website, both the classes and the slides. Okay, so thanks for joining.
Thanks a lot, Annie.
And we have to take our picture.
We have
We stayed in the picture. No, we need an Excel.
the person.
I'll put this to have a nice.
Look outside if there is.
Maybe we can ask someone passing outside. That's what I like.
I think yeah.
Okay, now you have done.
Yeah, okay.
Yeah. Thank you much.
Yeah. Stay in front. Let me see. I will then go, then we all. More or less. I'll go there. I know, but I will go
Okay.
Yeah, just take a few.
Over.
The wide angle telephone. Yeah, the second one.
Is here. At least you take the key.
Yeah, I will lock it. I will take this stuff here. Yeah.
Solo que tienen el. No, y esto aquí.
Ah, sì, sì.
Una vita lì.
Sì, sì.
E io considero che la sia.
Fare un po'.
Ah,